So, welcome everyone. Today I'm going to be talking about objective testing, obviously in the context of music technology. I will try to refrain from too much philosophical talk, which I will do in February. So we're going to get to the point of how do we test stuff. Now I would like to kind of open a little bit of a discussion, kind of get you into the thinking mode rather than the passive observer mode. So what do you think is the biggest challenge in testing audio gear? What is actually our biggest challenge? What is the holy grail? What is the unattainable stuff? Yes?
Is it the objective listening of each person?
Well, now we're talking about testing. So we're not talking about, perceiving. We're not talking about psychoacoustics. We're not talking about variability in the audience, how people hear stuff. So there's no subjective dimension to it. It's actually coming down to testing stuff. So the question is there anything, actually, is there anything that we cannot test? Is there any trick? Because obviously, no, we have all this gear already. We're born into this world with compressors and speakers and stuff, and it's all great. But do we see a pitfall in it all? Well, that's the only philosophical bit that I've prepared. Because to me, the biggest audio challenge seems to be, how do you test the measuring equipment? Do you get that point? And it's not just me playing around with feedback in kind of statements. It is actually a fact that how do we test the measuring equipment? You see, because we know by now, probably you know already, that we have things like microphones, and then we have things like measuring microphones. Okay? So we use the measuring microphone to measure the microphone or a speaker, but how do we measure the measuring microphone? Well, using another measuring microphone, and how do we measure that? You see where I'm getting at? So in a way, it's a funny thing, because actually I would claim that we are psychologically motivated to find the environment reliable. And through that process of motivation, we create science. Yeah? So I hope I don't get sacked for this, but actually I would say science is assuming. And in math, we call this axiomatic, which means that there is no way of coming up with anything unless we assume certain things. And mathematicians will tell you that if you assume that the two parallel lines meet at infinity, there is a different set of conclusions from that compared to the classical one when parallel lines don't meet ever. But if you understand this problem, you should kind of get, okay, well, wait a minute, where is the infinity, and what are lines, and what are parallel things? These are all assumptions. You see, so we have a certain set of assumptions that allow us to build a kind of a deductive pyramid structure, kind of inverted pyramid structure, whereby we come up with what we call scientific. But it's important to remember that it is axiomatic, assuming. So we have certain things that we cannot test for. We just say it's the way it is. Yeah? The other thing, the science is somewhat arbitrary. Logicians will tell you things about this because we do have multiple logics. So the one that we operate with, the way we think in terms of if, then, in terms of and, or, all these logical gates, seem to be just arbitrary set of rules that provide us with all the rest, but a different set of rules would do just as well. So we do have multiple logics available as well, no matter the fact that there is one which really kind of feels right and real for us. Yeah? But as far as the logics go, there's multiple. So it is a bit arbitrary. The reason I say somewhat arbitrary is because obviously it's not completely arbitrary. It has everything to do with us being kind of advanced monkeys. That's why this logic kind of really suits us. And the last thing I would also say about science is that it's very often conservative. And my best example here is the wave-particle duality. So you will still see scientists who are saying, well, it's a bit like a wave and it's a bit like a particle, but as soon as we have realized that there is a kind of fuzziness between what we consider to be waves and what we consider particles, if we were not conservative but progressive, we would immediately come up with a new term that covers both things. And we wouldn't be bothered anymore, is it solid or is it not, because it's neither. You see, the experiments tell us how things behave, but we have two models which we understand and which we cannot let go of. You understand? So the point is that we are conservative also due to the fact that it's the way we think. You see, once we acquire a way of thinking, it's really difficult to kind of discard it. Okay? So I was just trying to bust the myth of, you know, science being this solid thing that we can rely on, that's, you know, truth-seeking and all of these things. Okay? And then one positive thing, occasionally reflective. Yeah, science. It's a beautiful thing. Okay, so this is a bit of an intro, kind of get you to think. But actually today I'm going to get to pretty concrete things. So first I'm going to talk about tools for testing audio here. And then I'm going to talk about different types of tests that you might find interesting and useful. So in terms of tools, first of all we have hardware tools available and necessary. The first thing that came around that was a miracle was an oscilloscope, actually an oscillograph, which allowed to kind of trace a waveform on a roll of paper. And even today, you can measure quite a lot of things with an oscilloscope. I'll show you a few examples of that. Now, the other thing that we are often using in music tech for testing is an Spl Meter, which is a calibrated device that gives you the sound pressure level in your environment. So it has a microphone, it has a little battery, and it reads out the sound pressure level. Measurement microphones, as I've mentioned, so they are typically made to be very flat response and kind of very low directivity. And one other thing, there's by the way plenty more possibilities that we actually have in-house, is a Prism Sound D-scope. So this kind of goes back to what I've just said. Actually, this is the sound card which is used to measure the accuracy of sound cards. So it is a kind of the measuring device, which you kind of assume is the most precise thing, but you don't have anything to measure it with. Are there any ideas? So how do we actually deal with this? How do we specify what is the measuring device if there is no other that can measure it? What is the clue here? What makes it actually work? Because we know things actually work. We fly planes and all of this. I'm not completely throwing science out to the garbage. It has to do with reliability and repetition of stuff. Right? So if this sound card, you know, kind of is consistent in certain ways, then we can call it a kind of a measurement device. Yeah? It has to do with consistency. But it's important to understand it's not only about what you use to measure. It is also when do you measure stuff. Because we kind of assume that things are invariable in many ways, and in measuring, in other experiments, as you know by now, it's always very important to reduce the amount of variables. So to try to, you know, kind of pinpoint to focus on the thing in question. Are you interested in anecdotes about the time of measuring? Probably my favorite one is, I was in love with a girl at some point, and she said, oh, but you're always so kind. And I'm like, how do you know? She's like, yeah, well, I've never seen you, you know, be angry or anything like that. I'm like, yeah, but that's your perspective, because when you're around, I'm always kind. If you see me with other people, I'm horrible. You see? And that's the point. You see, you always have to also think about, okay, is my perspective a valid one? Do my measurements actually cover all the possible scenarios? And in this case, obviously not. Okay, so about software tools that we can use. Again, many more hardware tools. There will be many more software tools than what I list. First up, I have a fuzz measure. This is a kind of easy-to-use software for acoustic measurements and a few other things. We have it in the labs, in the studios, on the computer, and I'll actually be showing you some of that. For those of you who really want to get into science, actually MATLAB is the platform which has all the complex things available for you. You just have to figure out how to use them. It is a bit like a syntax-based programming language, but is indeed made for mathematicians, and it can do a lot of funky stuff. As far as acousticians go, most of them swear by this program called SMART. We don't quite have access to it, but it might be useful to know. For those of you who, there are actually free options as well. I think you pay for these. Room EQ Wizard seems to be the kind of best option on PCs. We've used it as well. It started from kind of room EQ software, but it actually grew into a kind of free software for a variety of testing. And obviously, one of the tools that I really like you to have available is skepticism. So you have to be balancing the proving and disproving of something. Very often, this is what we inherit from the lovely marketing world, is that we are keen on proving something to the extent that it becomes this. It's just obviously, you know, biased like that. If you see someone, he's like really trying to prove his point. What we do as scientists, as skeptics, hopefully, is we invest the same amount of energy into proving and disproving. If you don't do that, you're just not doing science. You know, you're emotionally latching onto a supposition, and you're really pushing to kind of prove to everyone that it's true. Don't do that. If you have a hypothesis, make sure you are trying to disprove it just as well as prove it. Okay, so those are the tools for the testing. And now let's talk briefly about the systems that we test and the type of tests that we have available. So first thing, I will talk about transfer function, which is somewhat, how should I say, it relates to electronic circuits. So what you will see is, as I go through the lecture, there will be techniques that apply to electronic systems. There will be techniques that also apply to acoustic systems. And also more complex embedded systems, as you will see. So what is a transfer function? Now, in order to understand the value of transfer function, let's briefly discuss these two terms. So we have a term linear time-invariant systems and nonlinear systems. Now, the way I've structured this is that I don't really have too much explanation under the keywords. So if you don't quite get it from my current explanation, you probably wouldn't get it from my brief explanation either. But these are the keywords that will get you to a lot of different sources where you can learn about these things from different perspectives. So if you see a lot of kind of worryingly, uncomfortably new keywords, please know them and use these to kind of progress your research. Yeah, that's the point. So I will give you a certain perspective now. So these two things, these two terms cover a set of audio processes, really. So what we have with the linear process is that is essentially not going to produce distortion. It has no nonlinearity. It will not produce new spectral components. That's the key thing here. A nonlinear system will distort. So typically every system will have a linear range and a nonlinear range. So if I take an audio amplifier, if I use it sensibly, I will be using it in its linear range and it won't distort. If I really push it, I'm getting to the nonlinear range and it will start distorting. So typically most systems will have some nonlinear range and we tend to use them within the linear range unless we are Jimi Hendrix and we just, you know, distort the hell out of everything. Now, as far as the time invariance goes, what this means is that the system will respond in the same way no matter when you test it. So typically, you know, as far as our little audio gear goes, they don't behave different based on the moon phase or the phase of the day or any other thing. So they are typically time invariant systems. Okay, so that's a basic distinction. Now, the transfer functions themselves have everything to do with describing nonlinearity, because they will actually plot the function, and if the function is aligned, it's a linear system. If it has some kind of curvature, some kind of knee in there, some discontinuity, it will be a non-linear system. So what we actually do with the transfer function, we plot all outputs for all feasible input signal amplitudes. Because we assume that this system will not, that this is a memoryless system. So what we are saying is that no matter when, and no matter what the previous voltage was, if we put a voltage to this device, it will output that certain other voltage. So we kind of consider it a really reliable system, and what we do is plot all outputs for all feasible inputs. Okay? Now this is quite easy if you have one variable. So if you have a system like a distortion pedal what you would do is kind of send all the possible voltages to it, and you would plot the output, and you will see when it starts clipping. Is it a kind of a soft clipping curve? What does it actually do? Does it have asymmetrical clipping and all of that? So it's easy if you have one input, one output, but as soon as you get multiple inputs, you can imagine the dimensionality of this transfer function grow. So for us, we'll probably be looking at the single inputs. So what are the applications? Well, you can detect electronics anomalies, so you can kind of test around circuits with this idea, and you can classify distortion effects. That's pretty much what it comes down to. How do you do it? One way is XY scoping. So if you have an oscilloscope, an actual hardware oscilloscope, it normally has two inputs, X and Y. And what you can do is you can put the input to 1. Well, if you have this black box system, the input goes to the X of the scope and the output goes to the Y of the scope. And it will actually plot this relationship. And an easier thing to do if you don't have an XY scope available, you can actually send a sawtooth wave through your system. If you send a sufficiently loud sawtooth wave, you understand sawtooth wave runs from the minimum value up to positive, and it kind of drops dead again and then runs up slowly again. It actually goes through all the values, you see? And if you just look at the waveform that comes out of the system that is being fed a sawtooth wave, you will see if there are kind of corners, kind of rounding off, a bit of soft clipping at the end. You will potentially see if there is an anomaly around the zero crossing. What you do have to make sure is that you send a decent amplitude voltage of the sawtooth wave. Yeah? So if you want to test the guitar pedal, go beyond the normal range just to make sure that you actually reach the limits. In electronic system, what you will find is that the limit, the actual hard limit, is the power rail. Yeah? So all these electronic circuits, they have their power feeds, and by law, by theory, by definition, you cannot exceed those voltages within those circuits. So if I have a 9-volt battery thing, I'm not exceeding that voltage. If I have a 12-volt adapter going into my effects unit, then my effect unit won't exceed the plus 12 voltage, which means feed it a sawtooth wave that goes up to plus 12. Just to see what it does within its range. Above that, it doesn't really make sense because this circuit is not capable of that. Okay, so that's the transfer function. So I'll have a few more of these, but at the end of each one, I'd like to stop for a second and hear if you have any comments, questions. Does this trigger any remote memories? Triggers? Okay, cool. Yeah? Well, that was just a laugh. Okay, so after transfer functions, let us discuss the dynamic range. So dynamic range is a term that covers many things. One thing in common is that it refers always to a dB scale, which allows you to measure relationship between two magnitudes. So you probably know this already, worth reiterating. What dB scale allows us to do is set up a number, come up with a number that is not an absolute value, it is not a magnitude, it is a relationship between two magnitudes. So in acoustics, obviously, you know that there is a kind of, there is a standard, there is a calibrated dB scale, which allows us to say that, I don't know, 120 dB is the threshold of pain, but that already has a reference point. Yeah, that's why it works. But in general, in a wider picture, the dB actually allows us to do anything. So I could even measure the, I don't know, the difference in, what's interesting, the length of this room versus the width of this room. I can express the relationship of these two magnitudes in dB scale. So what would be the dB value of this relationship if the length and the width were the same? Just to test your current understanding of dB scales. So if the two magnitudes are exactly the same, what is the dB value representing this relationship? 0 dB. Yeah, exactly. So 0 dB means there is no difference between two magnitudes. Yeah? And then obviously if one is larger, one is smaller, we get into that. I won't go into the maths of it. Essentially it's a log of this ratio. So you take the two magnitudes, take the ratio, one over the other, take the log of that. Depending if it's magnitude or power, it's 10 log or 20 log. It's a bit of a detail. What I expect from you is to open up your perspective and just be aware of these things, because once you need them, you will hopefully know where to find them. So I won't go into too much detail. Now let's talk about the dynamic range of stuff, and first of all ears, which are extremely sensitive. So what we would call the dynamic range of hearing in this case would be the threshold of hearing, which is, I can hear very soft sounds, how soft they are, and the threshold of pain. Although you could argue I still hear them once I start experiencing pain, but let's just stay safe and consider this. I've actually failed to look it up, but I think it should be about 80 dB, is it? The actual dynamic range. So threshold of pain is absolute 115? 120, and the threshold is about 40, yeah? 30, 40?
Yeah, again, it depends on...
It depends. It depends on the frequency, it depends on many other things. But in general, this is what we're looking at. We're trying to understand this dynamic range. Indeed, if you were to look at the detail of this, you should be saying, but wait a minute, at which frequency? Do you assume that we have the same dynamic range at different frequencies? Well, you shouldn't be assuming that. It's definitely the case that we are the most sensitive around 1K. So that's where we have the largest dynamic range, and it kind of tails off on both ends in low and high frequency. Part of the reason why we have such an amazingly sensitive ear is that it has adaptive mechanisms. So it's not just a receiver. Based on what it receives, it changes the way it does that. Yeah? So we typically have kind of a frequency-specific adaptation. So when you want to hear a very specific pitch, it seems that the kind of the hairs around that frequency make it easier for the cells at that frequency to fire. There's a funny mechanism there. I won't go into details. I probably don't even know the exact details. And the other adaptive mechanism that we have has to do with loudness as well. So if you're starting to push in more amplitude into your ears, it actually changes the way you perceive stuff, which is something you might be aware from clubbing and the next day. So the other dynamic range that we are interested in, obviously here is sensitive large dynamic range, is essentially the noise floor, which is also expressed in dB in relationship to the threshold of linearity. Yeah? So what you're looking at, if you're testing an audio device, is similar thing, kind of the maximum and the minimum value. In this case, we consider the maximum value the threshold of linearity, so before it starts to distort, because normally systems would go on but induce distortion. And the minimum value then is the level of electronic noise. So you don't have an input into the system, you measure the level output, and then the ratio of 2 will give you the dB value, which is the noise floor of your system. Yeah? Actually, I should correct myself here. That would be the dynamic range of the system. Noise floor you can still express in a value that relates to the current or the acoustic pressure. Now, in digital audio, we also deal with dynamic range, and this dynamic range has everything to do with the resolution of our audio, the vertical resolution, if I may, which is defined by the bit depth of our signal, which is defined essentially by the resolution of the numbers that represent the signal. So if we have a 16-bit signal, it means that each number is represented by 16 bits, 16 zeros and ones, and this gives us about 16,000 values, if I'm right, something like that, and that is a range of 96 dB. So what you have is a way of expressing the maximum amplitude, the way of expressing the minimum amplitude, which is the least significant bit flipping, kind of the smallest signal you can represent in 16 bits, and then you do the same kind of math. You take the ratio, you take the log of that 10 or 20 times, in this case 10 times, and then you do get your dB value, which is around 96 dB. Yeah? So this is essentially what we're talking about when we talk about dynamic range, and indeed it's a kind of a term that can cover many different things as well. I've shown you a few examples. How do you do this? Well, we kind of discussed it already. You have to measure the two levels, and you have to do the math. In acoustics, you need an Spl meter to measure the level of something. In electronics, what we do is we take the RMS, which is the root mean square, which tells us everything about the energy of the signal, not peak amplitude. So make sure you understand the difference here. RMS gives us the energy of the signal, and peak amplitude, just the peak. And these two things are somewhat related, but they're not the same. Okay, dynamic range. Any questions, ideas, triggered thoughts? Okay, let's go on. So I've picked this term just because it's present overall. You've probably seen it already. The THD, the total harmonic distortion. A lot of gear spec will tell you what is the total harmonic distortion of a system. So this measurement has everything to do with nonlinearities, with essentially producing artifacts. So if you feed a sine wave into a busted or an odd system, what you would get is harmonics, intermodulation components, and you could be getting funky things like subharmonics and intermittency even. I didn't list aliasing here, which is kind of typical for digital systems. But in any case, what we're getting at is that harmonics and intermodulation are kind of happening anyway. They're the basic artifacts of nonlinearity. So harmonics stand for all the frequencies that are integer multiples of the incoming signal. So you feed the sine wave at 400 hertz, and on the output you will get the 400 hertz, but you will also get the 800, the 1200, the 1600, so all the harmonics, and are gradually rolling off in amplitude. Intermodulation has to do with a kind of interaction of the input signal, or interaction of components within the input signal. The simplest case is if you have two sine waves at the input at frequencies A and B, and what you will get as a matter of intermodulation is the sum, A plus B, that will come out of the system, and A minus B. So if you take, for example, two unrelated frequencies, let's say 100 hertz and 127 hertz, what you would actually get out of the system after nonlinearity, after some distortion, is 227 hertz and also 27 hertz. So both the sum and the difference. And you understand that these new frequencies are actually not harmonically related to the input frequencies. Now you may know that if you mix harmonically related frequencies, they perceptually fuse. It is very difficult to hear them as separate frequencies. Whereas if frequencies have no harmonic relationship, they kind of separate. You can't hear them. And that's one of the things that actually has to do with musicality, musical applications of distortion. What you normally do is you try to really, you're really playing with perception. You're not playing with harmonics and nonlinearities. What you're trying to make sure normally is that you shape the original sound. Because if you overdo it, especially because of intermodulation, what you will get is that you kind of hear the original sound in addition to it. So always try to kind of figure out, okay, what does my perception tell me about this sound? Is it a single sound source? Or is it a sound source with something on top, which kind of relates to the original, but they separate? And you will find that these are the most interesting points when things are just about to separate. That's the point where you really kind of transform the original sound radically. Okay? And then I've listed these two here, subharmonics and intermittency, just to know that you can get really funky stuff out of the distortion as well. Certain circuits will produce subharmonics. Intermittency, as far as the circuit kind of doing unexpected things at unexpected times, is something that you can achieve as well. For this, you would need active feedback. So as soon as you get your nonlinearity into a feedback loop, make sure that there is some gain in that feedback loop. You will start getting really crazy stuff if you're lucky. Okay, so now we looked briefly about this nonlinearity artifact, which gives us a good perspective to actually figure out how much worth does the total harmonic distortion have for us. The total harmonic distortion actually focuses on harmonics only. So what it does, it actually uses notch filters to pinpoint the harmonics that you expect there to be and kind of sums their magnitudes. And in the end, it is the ratio of the sum of the powers of all harmonic components. So if you put in a 100 Hz sine wave, you kind of expect a series of harmonics. You measure at those frequencies, you sum those powers. So that's one part of the ratio. And the other part is the power of the fundamental frequency. Yeah, so you relate the power of all harmonics to the power of the fundamental, and that's your total harmonic distortion. You see, it doesn't tell us anything about intermodulation, which is more responsible for perceivable, audible artifacts. And of course, it doesn't tell us anything about any intermittent stuff that might be happening in the system. So the application of THD, in my perspective, is marketing gear. You see it all over the place. I wouldn't say it's horribly informative. It's kind of an easy way to say, oh, that device is less noisy than this one, or sorry, less distorted than this one. But actually, what I would suggest, instead of going through the trouble of measuring the actual THD, which is a standard ISO kind of measurement, have a look at the detailed harmonic distortion plot. Yeah? So I've mentioned the D-scope, which is a kind of a hardware device made for measuring gear, kind of really professional device. Actually, it's a really trivial thing to measure total harmonic distortion with this because it has a kind of a preset. It goes through the frequencies, it goes through the harmonics, sums them, does the ratio, does the dB. So you could be doing this easily. Yeah? But I would say, don't worry much about it. Look at the total harmonic distortion. Look at the detailed harmonic distortion plot. So let's look at one of these things. So here is fuzz measure. Did it just erase what I've prepared? Studio Classic Lab Sound. All right, so the measurements are gone here. So I will have to try and remind myself. Let's see if it will measure. So what I'm here it is. So hopefully we get a little measurement from here. Here we go. So what I've measured now, you've heard the sine sweep, is the actual response of these speakers and this microphone in here. And you kind of expect that it's not great, and it is not. Now the thing is that, let me just see, because I've prepared this, but it kind of erased everything. Let's see, where do I get all the different graphs? I think I might have to do a new from template live acoustics, advanced acoustics. Let's do that one. Because it has all these presets, obviously, to make life easier. Okay. So hopefully one of these, oh God, let's see, where can I select these things, right? So what I'm looking at is harmonic distortion. This is the one that I want, really, and here it is, okay? So what I have here is actually a plot of the amplitude of different harmonics as the frequency goes up. If I'm right, I don't see the legend here. This would be the amplitude of the fundamental, and this would be the amplitude of the harmonics. So what you see is actually that you kind of get quite a lot of distortion in the low range. The harmonics are all typically as loud as the original signal. And then in the mid-band, it kind of works out pretty much. But you see that it's quite irregular. What you also see is that the peaks in amplitude also come back in the harmonics plot. Yeah? Typically what you would want, obviously, is a flat fundamental and kind of as low as possible harmonics right there. And if you look at this, it tells you a bit more than just a total harmonic distortion. Because with the total harmonic distortion, you have one number which tells you the overall thing, whereas here you can actually figure out, okay, do I have a problem in bass frequencies? Do I have some resonance frequency problems? What is the system actually doing? So that's a really useful plot. Cool, so that's total harmonic distortion. Any ideas, questions about this? Cool, so after that, what I have for you is essentially a spectral response. So this is the bit that you might know something about. This has everything to do with FFT. Now, FFT is a huge chapter. You probably spend a month on it. So it's quite tricky to compress it like that, but I'll do my best. So what it stands for, FFT, is fast Fourier transform. And what it does, it estimates the spectrum of a signal. So it is the process that gives you the spectrum that tells you what is the energy at different frequency bands. Now, the way it works is that it produces spectral bins, and you can have a chosen amount of spectral bins, meaning kind of spectral bars, spectral entities that represent your spectrum. Now, typically with FFT, what you have is a frame size which is a power of 2, like 512,024. You might have seen these already. And you will get that amount of spectral bins. Unfortunately, half of them you can chuck out. But the frame size of your FFT has everything to do with the amount of spectral bins. Okay? So the amount of points that are measured across the audible range. Now, the important thing to understand is that obviously you might say, well, I want better resolution, so I'm going to increase my frame, my FFT frame or window size. I think there might be a few more terms covering the same thing. If you increase your FFT frame or window size, you will indeed get more spectral bins, more measurement points, so to speak, across the spectrum, but you will lose something else. Someone knows already? If you increase your frequency resolution, you will be compromising your time resolution. You see, because the frame size in FFT actually has to do with what is the size, what is the chunk of the audio that you're analyzing. See, the point is that the funny thing about audio, in a way, is that in an instant of time, whatever that may be, the shortest kind of conceivable duration of time, there may not exist very low frequencies. For a low frequency to exist, you need a lot of time. You need this oscillation to happen. So if I want a sub-bass, yeah, well, obviously I need cache more than time, because I don't need that much time. I need maybe a 20th of a second. Yeah? But in other terms, it is a significant duration of time for us, 20th of a second. Yeah? So the point is that if I look at a very small frame of audio, there is no low frequency in there. Yeah? So if I want to analyze my frequencies and capture the bass, the sub-bass, I really need a larger frame. Yeah? So if I have a 20 hertz signal, that's one period duration of 50 milliseconds. Yeah? Which is a 20th of a second. So I need at least that much time in order to capture 20 hertz. So that's one issue. And the point is that if I have a large frame size, then I don't know when things actually happen within that frame. So if I increase the spectral resolution, if I increase the resolution of my frequency axis, I'm actually losing on my time resolution. Does that make sense? And if I really make the frame very small, then I know more precisely when a transient happens, when a certain frequency becomes prominent, but I have a little resolution to tell which frequency that exactly was. It's a kind of a tricky thing where you have a trade-off. Right? And that's important to understand from a practical perspective, because depending on what you're testing, you want to choose different frame sizes. If you have a kind of a non-percussive, kind of a drony thing that you want to analyze the spectrum of, then you're safe to take a really large frame, you get a good frequency resolution and everyone is happy. But if you have, for example, I don't know, a quick arpeggio going, yeah, and you take a large frame size, just to be able to tell apart the frequencies, what you will have is that the two notes may be blending into the same spectrum because you're losing time resolution. Suddenly your frame captured two notes, and they are both present in a single spectrum, no matter the fact that you well know that they came one after the other. Does that make sense? So that's the kind of basic thing about understanding FFT spectral bins, is that you have this trade-off between time and frequency resolution. Okay, so let's talk a bit more about the bins themselves. What is a bin? Well, as I said, it represents a single spectral range. And in doing that, it represents it with two numbers, important to know. One is magnitude and the other one is phase. So when we look at spectra, we normally forget about the phase and look at magnitude only. And so if you have a spectral plot, the vertical axis is amplitude, horizontal axis is frequency, so you can read out that for a certain frequency, what is the amplitude within this system? What is the magnitude? Now the phase is something we don't look at because it's complex, it's wrapped, there are ways of unwrapping it, ways of actually making sense of it. And I won't talk much about the phase information. Technically it just means that that very frequency has a certain phase to it. But if you think about it, it kind of contains a lot of frequency information as well. So you see the spectral bins come at a certain interval, which has everything to do with the frame size, by the way. So let's say I have a spectral bin at 100 Hertz and at 150 Hertz, 200 Hertz, and so on. You can imagine this situation. Now the question is, how does my spectral representation encode something in between? 120 Hertz, for example. Well, in a magnitude plot, what you will get is that the 100 Hertz has some energy, and the 150 Hertz has some energy, because it's a kind of approximating that, but you can't really read out the 125 Hertz. Now, only with phase information you can actually come to that, because what you will have is that the 100 Hertz signal, or I should say the 100 Hertz bin, is able to represent the 125 Hertz signal. How does it do that? Well, the 125 Hertz signal has a shorter period, it's a higher frequency. So actually what you do, what the system can do, is say that, well, it's a 100 Hertz signal, but on the next frame I decrease the phase. You see? So actually what you're doing, you say, well, it's 100 Hertz, and the next frame I decrease the phase, which means I kind of pull them closer together. Next frame I do this again, next frame I do this again. So overall, I get the higher frequencies because I keep squeezing in the audio from the next frame. You see, so in that way you can kind of get to how actually a lot of frequency information is still encoded in the phase, because for this to be possible, I have to have a phase that is constantly changing. But that actually happens, that is how the system encodes all the intermediate frequencies as well. Interesting experiment, by the way, if you take an FFT and an inverse FFT, so you get from audio into the spectral domain where you have amplitude and phase, and then from those two you get back to audio, you can do some interesting experiments. The simplest thing is, if I remove all the phase information, just chuck it out of the window and resynthesize from magnitude, and compare that to resynthesizing from phase and chucking out the magnitude, what you will find is that the sound remains much more recognizable through phase information only. If you keep the magnitudes, chuck out the phases, very likely you won't recognize the sound source anymore. The other way around, you're much more likely to recognize what was happening. So in a way, you could even say that more necessary information is encoded in phase than in the magnitude. Okay? So again, FFT is a huge, huge chapter. I won't go into further detail. What I want to go into, though, is a kind of FFT over time. So the FFT itself, as I said, gives you these two things. Normally, we look at magnitude only because it is informative to the eye, to the visual self, whereas phase is much more complex. So we look at the magnitude, it tells us something, but again, it has to do with a single frame in time. And then if you want to understand or see more about the sound, then what you would want is a kind of a movie, not a single frame, but multiple frames as the time progresses. And typically what we have then is a waterfall plot. So fuzz measure is cool with waterfall plots, and here is one. Oh, sorry, that's not one. Oh, sorry. I have to get out of the full screen mode here. Okay, here is fuzz measure, and here is a waterfall plot. Okay, so what does it do? Well, actually one slice of this plot is thus a spectrum. So vertical axis is amplitude, and horizontal axis is frequency. So you see these are frequencies here. So what you see essentially in this case is the impulse response, so the kind of the spectral response of the system. I'll talk about impulse response later, how it develops over time. So essentially what you have is a kind of a energy impact. We'll talk about impulse in a bit. This is what it does immediately, the system, in terms of response, but it's important to understand that certain frequencies will ring on. And this is what you see. So if you're really buying a loudspeaker, you don't want just the spectral response, you really want to see the waterfall plot. And by the way, every loudspeaker that has a port, the kind of a reflex port, the kind of a hole in the box, will produce a lot of garbage in terms of this low frequency tail. Only sealed boxes will give you a neat kind of, in time response. So what can we see here? Well, these are milliseconds here. I go from 0 to 2,000 milliseconds to 1 second. So actually you see that my speaker to microphone in the laptop will ring on for more than a second at around 100 hertz. And so if I do an impact, 1. That's a whole lot of time. You see that actually the other frequencies, what is this? This is about 150 milliseconds. So it seems that the most frequency will ring on for at least 150 milliseconds. And then there are a few special ones. So you see here, I have an issue at about, what could this be, 6, 7K. This rings on for more than 200 milliseconds. So this is your waterfall plot. It is much more informative than just a single spectral plot. And with tools like this, it is really easy to get to it.
Zach,
yes?
Where do you get fuzz measures from?
So in the studios, it's there. It's installed on the machines. In the labs, it's not there. If you want it on your laptop, I believe there is a demo version for a month, so you can use this for a little project that we will set as well. Yeah?
I'll just agree with that completely. Waterfall plots, in terms of explaining fully what is happening in any system, are the best way to go. They really do show you what could be hidden further along in time. Even with critical listening, I use these and have done before to identify systems that you can hear ringing and are not showing a simple magnitude plot, and it's not until we have the waterfall plot that we really begin to understand where that problem is.
Yeah.
They are very, very useful.
We love the waterfalls.
We do. We do. So anyone thinking of doing speaker testing, any point building and testing speakers, yes, waterfall plots at the very least.
Imagine it being a chocolate waterfall. Okay, so here we are with the spectral response and waterfall applications. So as Nat said, microphone and speaker testing, measurement, definitely. You can test all sorts of devices. You can assess linear time-invariant systems as well, typically filters, things that can be matched with convolution. You can estimate audible artifacts, probably the best you can do with the waterfall plot. Now, the methods, what you heard just now when I did this test was actually a sine sweep. But you could come to a spectral response through using white noise or an impulse. Now, white noise and an impulse are spectrally flat signals. So it kind of makes sense. You put in something that has energy at all frequencies, and then you see what has been removed. The sine sweep is also a broadband signal over a larger chunk of time, but that makes it slightly more precise. Yeah? So you don't ask the system, you don't give it a burst of kind of flat energy, and you kind of in an instant check out, okay, this is what has remained, but you actually go through different frequencies one by one and see what's going on. So it's slightly more accurate, that's what you've heard here. But for those of you who want to go deeper into science, there are further techniques, there are actually variants of this technique. The maximum length sequence, which is essentially kind of a fixed looped noise signal. I won't go into the math of this, but it is more robust than the sine sweep. I mean, obviously, most software will be using sine sweep. It's just good to mention that there are better ways of doing this as well. Okay, so that's the spectral response. This is probably the most kind of crucial thing in terms of understanding the trade-off between time and frequency resolution and being able to interpret a waterfall plot. These things are really useful. Okay? Any questions, comments at this stage? Cool, so let's take a 5-10 minute break. I think this is a good idea. I'll go grab a cup of tea. Shall I bring in a pot of tea? I do this sometimes, kind of a big pitcher full of tea. Are people up for that? Yeah. Okay, I'm bringing a pitcher full of tea.
Like you need a massive.
Okay guys, so back to testing audio gear. So we hopefully have a decent picture of what spectral analysis gives us, what the spectral response is. So let's just talk briefly about this. Will a spectral response tell us anything about a distortion characteristic of a system?
Yes.
Yes. Gotcha. Not at all. It's a funny thing, actually. By the way, this morning I've double-checked with David just to make sure that this is the case. David is our kind of brain of DSP and, you know, engineer. He's actually had I'm not an engineer by vocation. I'm really sympathetic with it, and I love it, and I know much about it, but I haven't been trained formally as an engineer, whereas he has been. So I was just making sure, and it indeed is the case. What you have is, if you have a linear time-invariant system, which does not cover distortions and does not cover anything that has a delay to it, because with a delay it would be time-variant, the behavior would change over time. With linear time-invariant system, what you're actually covering are filters and complex filters. And this is what you capture with the spectral response. Why is it that a distortion characteristic will not be captured? It has everything to do with distortion normally being very amplitude dependent. You see, if I talk about overdrive as a type of distortion, what I'm actually having is a system that if I drive it, you know, at moderate levels, it is actually linear or close to. The distortion comes in once I overdrive it. Yeah? And you should kind of be able to see this, because a single spectral representation, a spectral response plot, an FFT plot, tells me how system responds in terms of different frequencies, but it does not tell me how the system responds in terms of different input amplitudes. And that's the point, because if I have a distortion process, let's say more generally, what I will have is a different response at different input levels. That is the point of distortion. That's how it comes about. So that's why a single plot won't really do it. And the other thing that a spectral plot won't do is it won't highlight my harmonics. Yeah, so it kind of blends everything together and says the output signal is hilly like that, but it doesn't tell me how much of this is actually harmonic distortion, how much of this is newly generated spectral content, and how much of that is just the shaping, which is caused by the filtering. Yeah? So that's the point. If you are dealing with a system that you expect to be nonlinear, to produce new harmonics, actually a distortion, or for that matter, if you're testing, you know, a microphone at the limits of its abilities, because you can push enough acoustic power into a microphone to distort as well, If you're doing that, make sure you don't just plot the spectral plot, because it won't tell you much about the nonlinearity itself. So there's different ways of doing this. I have some patches as well if you're interested. Obviously, anything you do in terms of testing, talk to me by all means. We also will have in applied audio systems, we have an assignment that goes into testing into some more detail. So we will be dealing with this. What I was trying to say is that I do have max patches that do certain tests that the software that I've listened doesn't do. And one of the most trivial things that you might find useful is just, it's not a sine sweep in frequency, but it's a sine sweep in amplitude. So I have a fixed frequency, and what I do is I drive this signal into the system and make it louder, 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 go up in amplitude. And then on the output, I just plot the actual amplitude coming out. And typically with an electronic system, when I hit the, it's not the rock bottom, it's the blue sky. What is the opposite of hitting the rock bottom? The ceiling. Yeah? So once I hit the ceiling, you will see that even if I push in more energy, at the output it's starting to get capped. You kind of get this kind of, okay, that's where I'm losing it. Yeah? And that's a simple thing which produces one plot, but then you can do it at different frequencies, and then there's different things you can do. What you could also do, for example, is you can take a broadband signal, so I could take white noise and do the same thing with that, such that I keep increasing the amplitude as it goes into the system, and then plot the output of that, so you kind of get an estimate of the system response for the whole spectral range. Yeah? So there's many different things we can do, and obviously I'm really happy to discuss the details of what you might have in mind. Okay, so what was then, just to conclude this bit, what is thus the way of figuring out something that distorts, something that is nonlinear? It is not a spectral response. One thing we've looked at is the transfer function, which can be informative, especially if you're classifying distortion effects. But if you really want a detailed look at things, you want some kind of a plot that has an amplitude axis, a kind of input energy axis to it. You want to see how does the system respond at a variety of input levels. Yeah, that's the crucial thing for distortion, for nonlinear systems, that they respond differently at different input levels. Is that cool? Okay, so from here, let's go on to the impulse response. So we looked at the spectral response, which is essentially, what does the system do if it receives a broadband signal? What does it do to different spectral ranges? This is all about the output of the system upon receiving an impulse. An impulse is a single burst of energy, kind of a single non-zero sample. Actually, there are such things as band-limited impulses. There's different things here. I won't go into much detail. The crucial thing for us to understand is that it allows us to deal with reflections. Okay? So we've dealt with systems that typically have a kind of reliable spectral response, time-invariant, don't distort, cool. We've dealt with systems that have a crucial nonlinearity that will distort at some point. Now we're looking at systems that have this longer time behavior, the systems that will essentially repeat the sound that comes in. The systems that produce a certain kind of reflection. So what is can anyone name such a system? Produces a lot of reflections? Well, this very room, for example. And so what happens actually as I speak to you is that there is a direct path between the sound source and the receiver, but actually there's myriad other paths. So via the window, via the ceiling, via the floor, some obstruction here and there, the pillar. All these things will reflect the sound. So what happens when the sound gets reflected? Essentially, the distance has everything to do with the duration of time it takes for my voice to reach you. If I take a kind of a longer path, what I get is a longer time necessary for this to happen. So it is a reflection, and we notice it is a reflection because it arrives to your ear, let's say this is the point of your ear, later. Yeah, so that's the crucial thing about reflections, they just arrive later. So it is the kind of, it is almost like I'm duplicating the sound source millions of times and repeating it at different delay times with different amplitudes, because not only will the reflected sound be delayed in relation to the original direct path, it will also lose amplitude. Yeah, it will get absorbed. I mean, you can read about, it's one of those things I didn't really, I'm just going to mention them, but typically in acoustics you have a lot of ways of, or things to measure about surfaces, about the reflectivity, about the diffusion property of the surfaces. What you will have is that they will respond differently to different frequencies. They will absorb certain frequencies more than others, so on and so forth. The outcome of that is that as the reflections travel longer to reach the destination, they will, on average, be losing more energy. And in a typical room, this is actually an impulse response of a room, what you get is an increasing density of reflections. This is typically something you can check. Good reverbs will have this property as well. Send an impulse to your reverb, record the outcoming signal, and check if the reflections are increasing in density. Why do they increase in density in a real-world situation? Well, it has to do with multiple bounces. Yeah? So what we have typically also when we talk about reverb, artificial reverb, is that initially we get what we call early reflections. So they're typically a single bounce reflections of the first nearest wall and so on. But once sufficient time has passed, then the bit of energy that has traveled up to that wall and then to the floor and then to the ceiling, that wall and then to the destination, these will increase in density over time. Does that make sense? So as the time passes, there's more and more reflections coming in. This is what's happening. So this impulse response indeed allows you to analyze this. Check out how are the reflections in here. I mean, typically for studios, you know, the nice thing is that you can even kind of project the distance of a wall. You know, if I have a situation with a microphone and a speaker, yeah, obviously there is a certain time delay that has to do with the air, the speed of sound in the air. And then I have the next reflection, let's say 10 milliseconds later, I can actually calculate how much longer the path was than the direct path. And if I do a bit of geometry, I can actually figure out the distance of the wall. Works. Yeah? So it's a really lovely way of doing this. Obviously, we can test rooms with this, but we also test devices that typically have a reverberation-like response, delays, everything that has some kind of complex time response is very well analyzed using impulse response. Now, the funniest thing, and potentially mind-boggling, is that the FFT, so the spectral analysis of the impulse response of this signal as a waveform, if I just chuck in this impulse response into an FFT frame, get the spectrum out, I will get the spectral response. So actually it's a bit like walking a circle. Yeah, I can go around in both directions. So what I can do is I can measure the impulse response and from that get the spectral response, or I can measure the spectral response and from that get the impulse response. Yeah, because there is an equality between things. Obviously I won't go into much deeper than this. It's just useful to know that these things actually connect. Therefore, I won't list the methods for impulse response, because if you remember here with the spectral response methods, we already had this white noise impulse sine sweep and the maximum length sequence. So you've seen, actually you have not seen, let's see if we get an impulse response from the measurement in fuzz measure. Because you've seen that the way I've done this measure was just by a sine sweep. Yeah? And I can get an impulse response plot from that. You see, so I've done a sine sweep measurement, but it actually covers all these things. And this is the impulse response between my microphone and my speaker here. Reversing, Lori reversing. Huh? So you see what's happening. I mean, it's not great detail. I would probably need to export it as a waveform to really see the detail. But you see, there seems to be a very crucial reflection here. This one seems to be kind of related in time. It's almost like double that time. Who knows what it is? I won't go into the detail. For us now, it is crucial to get to understand that these things interconnect. Okay? So what are the applications of impulse responses? Applications are artificial reverberation. That's where you might have encountered this term before. So what you can do is, if you have an impulse response, if you measured an impulse response of the system, you just chuck it into a convolution reverb, and you get essentially reverberation that is modeled on this impulse response. So that's fairly popular. You can capture the reverberation of anything pretty much. Yeah? How can you do it? Well, as you see it with the sine sweep, could do maximum length sequence, could do a balloon pop. That's the kind of old way of producing an acoustic impulse, a gunshot, and potentially a few other ways. And one last thing I would just like to say about FFT. So now you see how it connects to the impulse response. It kind of binds things together. This term, orthogonal, is probably not very clear yet, and I would like to clarify it a bit. So what FFT, what orthogonality means in transforms, so FFT is a kind of a mathematical statement. And the fact that it's orthogonal, what it means, if I take an audio signal, a bunch of samples, do an FFT, get the spectrum, a bunch of magnitude values and phase values, and then do the inverse FFT, get back to the time domain, get back to the samples, there will be an equal, the two signals at the two ends are equal and identical. Yeah, so all the samples, there's no loss whatsoever. This is a mathematical statement that is called orthogonality. It's orthogonal. It does not mess up. It does not lose information along the way. This is fairly important. Okay, so impulse response, there we go. Now let's get to a bit more real-world scenario. So we've actually looked at kind of insides of electronics, certain effects. Obviously we've discussed rooms a bit, but we haven't discussed the kind of the user perspective. And from the perspective of the user, most of music tech devices will be characterized or can be characterized by defining the latency. So what do we mean by latency? What is obviously some kind of delay in response. And there's many causes for latency in music tech. First of all, we have acoustic causes. So in air and in solids and otherwise, sound waves take time to propagate. So a certain distance in space corresponds to a certain amount of latency. Do we know approximately what that is? Let's say you are 3 meters away from me. How long does it take for my speaking voice to come to your ears? It's probably not too long. Do you ever notice in your daily life that there is a latency in terms of sound traveling around? Anyone? There's one example that always strikes me. Huh? Lightning, yeah? Although you might say that it's not obviously causal. I mean, sometimes I will see a lightning and there's no booming, and sometimes there's booming without me seeing a lightning. So it's not necessarily causal. There's one thing where it really stands out, for me at least. It's when I see people playing football from a certain distance. So already at about 50 meters, like half the football pitch, like a small football pitch kind of from the audience, you can notice that you see the ball being kicked before you hear it. There's a kind of a latency there. And it has to do with the fact that the light travels much faster than sound. So it is an obvious phenomenon. If you really want to calculate with this, all you need to know is the speed of sound in air. By the way, it depends on humidity and temperature. What is the speed of sound in air? Anyone?
340 meters per second.
340 meters per second. So indeed, if I'm at a distance of 50 meters, yeah, that's about 1/7 of a second. Does that make sense? So if it's 1/7 of a second, it's something that I will notice. So that's what it is. And obviously, if the distances are larger, it is even more noticeable. So how about 3 meters? How many seconds would that be? Yeah, 100, about 100. So if you have, let's round it off at 300 meters per second. So 3 meters will be 100th of a second. Cool. So that's about acoustic latency. And in solids, by the way, in solids, sound travel faster. You can make funny installations using this principle, potentially. Then we can talk about the latency in analog audio transfer. So it's strictly the electronic aspect of this, the fact that the electrons have to travel through wire. I was meaning to look it up, but I didn't quite. I wouldn't know what 10 meters of wire cause in terms of latency for an electronic signal. But do make a difference here, because acoustic signals can travel through solids, but here we refer to an electronic signal. So it's a slightly different thing. Yeah? If anyone wants to look it up, I'll be very curious. I mean, you might know that audio hi-fi freaks, they would actually make sure that the cable length is exactly the same between the amp and the speakers, just for this potential delay. And if you want to bust their myths, just measure it. Figure out, how many microseconds would it take? And then you start asking the question, okay, well, what is the measurement device that will operate at this level? Yeah, get there. We are skeptics, yeah? We don't believe anything. You don't believe what I say, please. Don't trust me, yeah? I'm trying to make you question things and research things, go after things, discover things, not trying to tell you the truth. Okay, so we've discussed that. That's electronics transfer. Then we have digital audio transfer. So it's crucially different because digital audio is buffered and clocked. Yeah? And due to these mechanisms, we actually have much larger latency times. And then we get into funny areas because we can also discuss sensor reading. So now we're getting into kind of digital instruments where you actually interact with the thing, you control the thing, you press and it makes a sound. Here what you get is a little issue with computational priority. So what happens is that typically an operating system, a computer, will have a set of priorities, and the sensor reading is typically not one of them. Audio, digital audio is, because if this buffering clocking fails, then a lot of things will fail. The whole audio system will collapse. But if the sensor readings are a bit late, there is jitter, I will discuss that. It typically doesn't bother people. By the way, an Amiga computer, do you know these things? Yeah, these old boxes that can't do much at all, they're still more accurate sequencers than the newest MacBooks. And it all has to do with computational priority. Because the way they designed the operating system, it is thinking that my MIDI signal is really crucial. Obviously it is, because it's one of the few things it can do. It cannot make graphics, it cannot make your icons jump around, change colors, motion, all of that. Can't do nothing like that, but it can definitely sequence the MIDI signal with some decent precision. Yeah? So that's at the kind of sensor reading MIDI stage of things. And then, worth kind of expanding the perspective, if you actually get embedded interactive systems, typically I'm referring to a little Bella thing, which is the least latent thing around. It can actually produce latencies less than 1 millisecond from sensor back to the audio. So you have a sensor reading the sensor, computing that, computing the audio, sending the audio back. It actually operates at buffer sizes of 2. Try to set your sound card to operate at a buffer size of 2, it won't even let you. I mean, most of the things, I think my RME collapses at 64 samples per buffer. So you understand that the buffering in digital audio is the main cause of latency, because what it does, it specifies the length of the buffer, the amount of samples that are treated as a chunk, which means that as I'm receiving the audio signal, kind of digitizing, I have to wait for the last element in the chunk to arrive. Yeah? Then I have this chunk and I process, I do all my little digital processing, and then I'm at the stage of outputting, and again, I have another delay because I actually have to send them all out one by one, and I have finished dealing with a single chunk only when the last sample has been played. Yeah? So this kind of buffering, chunking of samples is the main cause here. So in a decent, interactive, embedded, low latency system, you have really small buffer sizes. Yeah? So Bela does this very well. And then I've added here another source of latency, which is curious, because once you get to build really useful, playful, proper computer-based instruments, digital instruments, what you really want to include is tactile feedback as well. So typically, what we have at entry level is kind of vibration feedback, which you have in kind of the game console controllers, but it can get more complex than just vibrational feedback. By the way, it's not trivial at all in terms of being able to learn how to operate such a system. Tactile feedback is really crucial. Research shows that you can distinguish about 5 different frequency bands with just your tactile sense. This research came from the violinist claiming that they hear through their fingers, and then obviously we're skeptics that, of course you can't hear through your fingers, so we measured that, and we figured that you can't really hear, but you can distinguish certain frequency ranges. Yeah? Okay, so obviously if you have this as well into the system, so obviously you have a sensor, you have kind of sound synthesis that comes back as audio, but from the sensor you also get tactile feedback. It kind of increases the latency in the system. It is something worth measuring. Okay? Now, so this, everything, all of this has to do with the kind of absolute value of latency, how much delay there is in a system, but you will find that the jitter, which is the irregularity of the latency, the kind of the variability of the latency, can be very, very crucial. So it's worth measuring. Typically, if you have clocks, then their jitter is quite crucial. So also for sound cards, for example, the jitter of the clock, of the digital audio clock, is crucial for the quality of the sound. So what you will see people do, for example, is have a master clock in the studio. So you will find configurations whereby you can spend tons of cash on the master clock and less cash on your ADDA, and just by using, I don't know, cheapo M audio or whatever ADDAs, if you clock them better, they will sound better. Yeah, so the clocking is quite crucial. Now, in terms of embedded interactive systems, it becomes even more important. It was shown that, you know, in kind of digital instruments, it's very crucial that you have an instant response. And we can measure this, we can ask people, okay, how does this feel? Does it feel immediate or not? And what you will find is that the absolute amount of latency is less crucial to the experience of immediacy than jitter. So if I have a reliable latency, let's say of, I should be realistic here, let's say I have 10 milliseconds latency, but it's always 10 milliseconds, it doesn't disturb me as much as if I would have a variable latency between 2 and 6 milliseconds. So overall less latency, but the fact that it's changing is really disturbing, because we can compensate for some latency, but we cannot keep compensating like that. The reason why we have a lot of jitter, and this has to do especially with kind of combining MIDI and audio, is that the MIDI does not have enough priority. So what happens is that a MIDI signal is being handled as audio blocks come and go. So independent of when it happens, the MIDI input, it actually has to wait for the next audio buffer to start a process. If I'm playing a snare sound with a digital controller, depending on when within a frame 512 samples, whatever it is, let's say it's 10 milliseconds frame, yeah? No matter when I hit the snare drum within 10 milliseconds, it will start to get synthesized only at the beginning of the next frame. Does that make sense? Because audio cannot just get interrupted within a frame, within a block. So I know, okay, the snare sound has to be played, but I cannot interfere before the next block starts. Yeah? And if you have a system like this, it means that I will have a variable latency depending on when I hit the snare drum within that frame. Because if I hit it right against the end of the frame, oh well, it will start quite quickly after because the buffer is almost over. But if I hit it accidentally at the beginning of a frame, then I will be suffering all this latency. So actually in designing such systems, what you do, believe it or not, is you fix the latency. So you say, depending on when I hit it within this frame, I will start it at a variable point in the next frame. So you're actually inducing further latency just to decrease the jitter. Does that make sense? Because jitter is more disturbing, the fact that it changes latency. So you're saying, okay, my maximum latency is the buffer length, but in my system I will make sure that every event gets that amount of latency. So even events that could be having less latency, I will make sure they have the maximum latency just to decrease the jitter. Does that make sense? That's what we're doing. So that's jitter. Okay, latency applications, digital audio workstations. If you have a kind of a digital mixer thing and everything, it is quite crucial because what you will have is that if you start mixing signals, audio signals, with some latency in the signal, you will start to get comp filtering. I didn't go into this, maybe you remember, maybe you've heard it already, but if I mix a signal with a delayed version of itself, I get comp filtering. I can take this for granted. So it's very crucial that the latency is well balanced and designed for complex digital audio workstations. And as you've noticed me, I've talked a lot about kind of digital music instruments. It is one of those things where it's quite crucial to have little latency. Methods, how do we measure latency? The easiest, most straightforward thing is to simultaneously record input and output. This can be easily done with a sound card. You have two inputs, you have left and right. Yeah? And then you can see it on the plot and you can go like, okay, this is where the signal comes in, this is where it goes out, that's the duration of time it took through the system. Easy and straightforward. If you are dealing with more complex embedded digital instruments, you can still use this technique because if I have, for example, a kind of a snare trigger, I can put a microphone right next to it for the left channel recording, and I can actually record the audio coming out of the synthesizer on the right channel. So actually an acoustic signal will pinpoint the moment in time when the interaction has happened. You see? Because I cannot, there is no other way to tap into this input. So the only thing that you really have to work out is how can you make the input available in an audio signal. And if you do this, it's plenty. Again, you know, the resolution of your measurement will have to do with your sampling rate. So if you're trying to measure really minute delays, you won't be able to do it with a sound card. Yeah, what is the time duration between two samples at 44K? It's about, what is it? Microseconds, 600 microseconds? Definitely less than a millisecond. And so we have 44,000 samples per second. 1,000 samples would be 1 millisecond. Yeah? So 44,000, so we get a 44th of a second. So it's about 0.02 milliseconds. It's a rather short duration, but you know, you can't measure the latency through wire with this. It just doesn't have enough resolution. Worth mentioning, in terms of me having low battery net, you have your charger. It should be fine, I have another 15 minutes. The worth mentioning is one thing you can do is obviously look at the plot and say, okay, well, this is the amount of latency. If you want to do this accurately, what you should be using is cross-correlation. Again, I'm just mentioning a keyword for your further research. It is a way of essentially superimposing two signals and figuring out their cross-correlation across different delay times. So the way this algorithm works is you take one signal, you take the other signal, you measure the correlation, so you kind of measure the similarity of the two signals, and then you shift them in time and do this again. Shift them in time, do this again, shift them in time, do this again, and then you get a nice little curve which describes the correlation of two signals at different time delays, and the peak of that curve will neatly highlight the likely delay time. May there be a very clear delay in the system. Useful technique, goes a bit over the top, but useful to know. Latency, any questions? Cool, so you understand that their latency occurs in many different domains. Depending on which domain you're looking at, you would have to choose a different way of measuring it. Cool, let's talk about directivity. So this is the thing that is now getting us more to into our acoustic environment. So I'm actually talking about acoustic propagation here. First thing it tackles, which is really important, is the point source paradigm. So please be aware that the way we think about signals is completely confined within this paradigm. We cannot think outside of it pretty much. And the point source paradigm tells us that in a single point you can describe the acoustic field. This is our simplification of stuff, because if I say, okay, I put down a 10K's worth of microphone in the middle of the room, everyone will agree, wow, what a high fidelity capture of the acoustic environment. Technically, no. Technically, it is a point source thing. We are capturing the acoustic energy at a single point in the room. What happens in the room is millions times more complex than that. So just bear this in mind. And when we look at the directivity, it sort of unravels this problem, or actually this feature. So the basic thing in terms of directivity that you've probably seen already is a polar pattern, which plots the magnitude of response versus angle of incidence. It's a pity I didn't get a little plot just so you see, but you know these things that you see in microphone specs, a kind of a circular plot, and then it tells you essentially what is the magnitude of response at different angles. What is the question? At which frequency? So you already should kind of start getting suspicious that a single plot like this won't be too informative, especially because the directivity has everything to do with frequency. You might know that the high frequencies are much more directable. A low frequency isn't. If I have a subwoofer in here and I play a 20 hertz tone, there is no way I could stop it from emitting the energy to the back, to the sides, and all over. It's a truly omnidirectional thing in that sense. Whereas if I have a 20K tone, well, I would never be able to verify whether I have one, unfortunately. But let's say a 10K tone with different cones and ways, I can essentially direct it really accurately and make sure that people behind the source don't even hear it, and people in front do. So the directivity has a lot to do with different frequencies. It also has to do with the physical environment, because the size of physical objects has everything to do with how acoustic waves behave around them, how much they get absorbed or not. So typically a base frequency, which is maybe 20 meters length, will find no obstacle in this very pillar, because it's just inside the wave already. It kind of, what is the word here? Like a plasmoid. It kind of embraces it, it sucks it in, it doesn't exist for it. And if I have a 10K tone, well, it just won't go through at all. If I have a 10K tone playing from here and I'm right here, I'm very unlikely to hear it. Obviously depends on many things. If it's a bass tone frame from, I will for sure hear it. There's no way that this pillar will stop a bass tone. Actually, it seems, I think it's 10-meter lead wall thickness that is capable of stopping like a 10, 20 hertz signal. It really takes a lot of matter to stop bass frequencies. Okay, so that's the polar pattern, magnitude versus angle of incidence. The other thing that you might have seen already in terms of directivity test is the off-axis response. neat microphone manufacturers will give you this. So it's actually just a spectral plot, but at a given angle of incidence. So you say, okay, well, on axis, this is my spectral response. At 20 degrees, it's slightly different. Right? And what you will find actually is that natural sounding microphones will have a great off-axis response. And most manufacturers won't give you these measurements. Question is whether they're making them to start with. Because what happens is no matter the fact that it's a very flat response on axis and I direct it to my saxophone player, the point is that the saxophone as a sound source is a very complex thing. It emits different spectral characteristic in all the possible directions. So actually the spectral characteristic that is reflected from the wall comes back to the microphone and then, you know, being changed by a bad off-axis response produces an audibly unreal sound. You see? So actually to have a good response, yes, that's what I need the charger. Oh, you don't have the charger. Anyone has a charger here? Well, I know it's
Type C, is it?
Yeah, it's a Type C. Oh, actually, yeah, you have one.
Yeah.
I've done this previously. The nice thing about this, Nat, you might be interested, is that you can actually run it off a phone charger as well.
Yes.
Yeah, yeah, did you realize? Oh, that's such a saver. Cheers, man.
So you know yesterday, and those of you who were in the lecture yesterday, wasn't it? And I asked you to be sceptical of the information. One of them there was that notion of off-axis response, and very few people will give you an off-axis response because they tend to look horrific. And a lot of manufacturers will measure all the information for on-axis, but soon as you get away from that sweet spot, that point source coming out, it can deteriorate rapidly. So your good manufacturers will give it you, but the others won't necessarily. So these are things to watch for when you are employing your skeptic's hat and looking through all manner of kit tech specs.
Yeah. Actually, I think DPA, they give you an off-axis response. Shups as well, yeah.
I would have thought.
Yeah,
If
exactly.
you looked at the shirts yesterday, there were a few. Can you remember if there was not off-axis?
I think there was, yeah.
I thought there was as well. So again, they really do take time to consider that not everything's going to be captured on axis.
Please. Please.
Is it going to lie? Is it going to come back to life in a year?
Well, the thing is that it's still complaining about having insufficient battery to even start up with. But all in all, actually, we have come to the end. That was the last slide in terms of directivity of stuff. I think you probably recall what was on the slide. So what you had is, first of all, applications. So everything to do with microphones, speakers, and such. And then the methods. So the methods are a bit tricky here because the way to measure this, first of all, you need an anechoic chamber. And then you are likely to need precision turntables and precision dollies. Yeah, because what you're actually measuring is how systems behave differently at different angles. So you have to be very accurate about setting an angle. So typically if you want to measure a microphone, you would have it on a precision dolly that you can rotate around, set an accurate angle of degrees, do the measurement again, and so on and so forth. Fairly meticulous thing. All right, here we go. So that's one thing about these measurements. I believe we don't have an anechoic chamber anymore. We used to have, back in the day when we had acoustics program as well.
We do have a little test room, which you probably all are.
We have the fridge.
We have the fridge.
Yeah, the fridge is a kind of fairly well isolated thing that
But
can.
it does have its own response. So be careful if you do
Oh,
go
yeah.
in there to do any form of measurement, that you have the measurement of the item and take the response of the room away from that rather than just.
So I have another few keywords here for you to explore. One of them is ray tracing. I won't go into the details. It's a very complex way of actually analyzing rooms and things, because you see, if you actually take the assumption, now we're kind of back to the particle wave duality here. If you take the assumptions that, you know, from a sound source, waves are traveling in all possible directions, you kind of get to the point of asking, well, how many directions can I calculate with this? You know, it's an infinite amount of directions, you know. It's a kind of a funny thing. You can do, so if you have a particle model kind of running, you can do this ray tracing, so you kind of, figure out something about the room. Things you can also measure is diffusion and reflection. That's more kind of acoustic stuff. We didn't go into that. And these are the methods applications.
Have a go at ray tracing. Have a look at it. It is a
Have a look.
fantastic, fun thing that enables you to really understand what's happening within a room.
Yeah. So finally, let's close with a mini project that I would like to set for you. So if you find any of this interesting, intriguing, motivating, what I invite you to do is test something, obviously. You've seen a few different things in terms of methods, in terms of gears, stuff that we can test, so pick your choice. To accompany this, I would like to see a report of about 500 words and neatly annotated plots and tables of data that you've acquired just to kind of be accurate about this. So this is all about objective testing, nothing to do with how we hear stuff. It is measurement. Yeah? If any one of you is really motivated to dig into D-Scope, which is the sound card for testing sound cards, among other things, by all means, Richard can lend you the D-Scope. The only one issue that I have personally with it, that it does not run on Mac operating systems, which kind of makes it a bit difficult, as I have this machine instead. It runs on PCs, but it runs very well.
And
Okay.
then plus measure, just to say that if anybody did want, it's going to be 33 quid once you've applied your educational discount.
Fuzz measure, yeah, it's not horribly expensive, no.
No, so if your personal license plus all support, £33 for anyone who is considering going further into more on the objective side this year and next year.
Yeah. One of the things that it can help you set up your room. Because what you will find, I mean, I guess everyone has a pair of speakers in their room kind of trying to mimic a studio setting. What you will find is that people will tell you that, yeah, treating the room is more important than most other things. But how you treat the room is something that can be very well informed by such quick measurements. One of the important things you can do is you can find a resonant frequency, normally kind of a low frequency mode that really messes your responses up. And what you can do is you can actually place bass traps at the quarter of the wavelength of that frequency. You can also create, if you're really interested, you can create Helmholtz absorbers. So you can actually create little cavities that will absorb that very frequency you have a problem with. Yeah. So if you want to be clever about this, and you're not just spending a few months in a room, you really want to have your studio sounding well, kind of running around with the measurement microphone, looking at, okay, in this corner I have a problem, that wall has a problem, that one doesn't. It really can inform your arrangement of bass traps and otherwise absorbers. Also in terms of fixing your sweet spot, fixing the distance from the walls, all of these things can be very well informed by running around with a measurement microphone.
Yeah. Or even I found just holding it and sort of spatially averaging over, if you know where you're going to be sat, you can also just spatially average just by sitting there with the microphone.
Exactly.
Give you a good indication.
And if you want to do this for your car, then that will help you even more.
And you definitely are in a well position.
Yeah. Cool. Thanks for coming, guys. Okay. And I will see you beginning of February, I think.
Yes.
First week in February.
For more philosophical stuff.
For the heavy stuff, yeah.